Hi everyone, and welcome to our discussion of section 7.5, wherein we will consider how to approach integrating a function that doesn't obviously present a method, or that you haven't been told which method to use when you're integrating. So we're going to lay out an outline of steps that you should consider, and then we'll go through that outline and we'll give examples of each of the steps. So step 0 is to have the table of basic integrals memorized. So there are going to be integrals that we come across in this class that are supposed to be integrals you just have in your head. If you have these integrals memorized, it will be much easier to work many of these problems because you'll get to a point where you have a pattern that you recognize and you can just write down the antiderivative instead of using technique. So there's a table on page 543 in section 7.5 that is a digest of all of the integrals that you're supposed to have memorized. And I would encourage you to try to memorize those. It's convenient to work off of the table, but if you have them memorized, then you don't have to spend time hunting through the table to try to figure out where the pattern is that you're looking for. Now the actual outline is simplify if possible, look for an obvious substitution. Many of the integrals that we'll see in this section and going forward in the class will be solvable with some advanced technique, but also with a simple substitution. And if you can do a problem with substitution, it will always be faster. 3, classify by form. And we learned a bunch of forms already that we can identify technique from the form of the integrand. When we go through the list in detail, we'll actually break this point down into all of its subcases where we can identify what technique we should be using by what the form of the integrand is. Finally, step 4 is keep trying. Just because one technique doesn't work doesn't mean that there aren't others that will. It's also possible that you might have to use more than one technique as you're going. A U substitution might change a problem into something where you can use an inverse trig function, for example. So now let's look at this list in more detail. How do you know what to do given what type of problem you're looking at? And I'm going to give some examples of where these techniques apply as well. And then in the example video, I'll try to walk you through the process of looking at an integral where you don't know the technique and trying to identify what kind it is so you can triage the problem. Step 1 was to simplify if possible. As examples of the sort of things that become easy when you simplify, the integral of the square root of x times 1 minus the square root of x. It's obvious here that what you should do is distribute the root x into the integral. And then you can just use the power rule, x to the 1/2 minus x dx. Slightly less obvious are examples that involve trig functions. So one of the things that you have to do when you're working with trig functions a lot of times, if it's not obvious how to proceed, you can change the problem into sines and cosines. So if you were looking at the tangent of x over the secant squared of x dx, if you reduce that problem into sines and cosines, you're going to get the integral of the sine of x over the cosine of x over 1 over the cosine squared of x. And this whole thing turns into the integral of the sine of x times the cosine of x after you algebraically simplify. And that you can either do with a U substitution, or you can do it with a trig identity by noticing that this is really a half of the sine of 2x. In either case, these are problems that become integrable once you apply algebra to them. For point 2, we want to look for obvious substitutions if we can find them, because substitution is easier than the other methods that we've introduced. Suppose that you were looking at the integral of x over x squared plus 1 dx. It's possible that you can integrate this with an inverse trig substitution. And in particular, this x squared plus 1 down here suggests that we could use an inverse tangent to solve the problem. But it's actually easier to solve this problem if we notice that we can let u be equal to x squared plus 1 and du be equal to 2x dx. Because in that case, du over 2 is equal to x dx, and this entire problem turns into 1/2 of the integral of du over u. This is much easier than using the arctangent. When you're looking at an integral, try to see if there's a way to turn it into a simpler integral using an obvious substitution. Substitutions are easy to check because if they don't work, it will be obvious when you look at the du. If you look at the du and it doesn't look like it will cancel algebraically all the x's in the original integral, then don't use that substitution and move on to another step. Step 3 is where you actually have to do the real triage work, which is to identify which technique goes with which form of integral. So we really have 4 different approaches past substitution that we picked up right now. We have integrals by parts, we have integrals where we've got trig functions, we have integrals where we notice a pattern we can use inverse trig substitution on, and we have integrals where we can use partial fractions. And what you need to be able to do is look at a function and identify which particular type you're looking at. If you see trig functions, then you're in the land of section 7.2. Sometimes there are patterns, odd powers of tangent, even powers of secant, odd powers of sine and cosine, or other techniques involving trig identities or changing to sines and cosines, but all of that technique was contained in chapter 7.2. Another thing that we saw was rational functions. Remember, the rational function is a polynomial over a polynomial, so no roots. For rational functions, we learned integration by partial fractions. And that was chapter 7.4. If we have radicals, and those radicals contain squares, then we're talking about inverse trig substitution. That's the content in 7.3. Finally, we have sort of a catch-all category for integration by parts, which really splits into 2 different cases. The first is if you have a polynomial times a transcendental function. So that is polynomial times e to the x, or polynomial times cosine of x, or polynomial times sine of x. Then we know that we're going to work by parts. And that was the content of 7.1. Now, it's also the case that parts is sort of your technique of last resort, which we'll do in point 4. Finally, point 4 is keep trying. So what goes under the category of keep trying? Look for a less obvious substitution. Or try parts. So there are integrals where there's no other way to proceed. They don't fall into any of the categories we've seen before. So, for example, here you could think the integral of the natural log of x dx. There's no other category that this fits into. It doesn't have trig functions, it doesn't have radicals, it's not a rational function, there's not an obvious u substitution. So the very last thing that you should try is the most powerful technique of all, but also the most difficult, which is integration by parts. Finally, in a lot of these exercises, as I pointed out, there might be more than one technique that needs to be used. So here you could think about something like the integral of 1 over x squared plus 2x. That was an exercise that came up in the homework. The first thing that we needed to do here was rewrite this as the integral of 1 over x plus 1 squared minus 1 dx. Okay, so that we have not done anything yet except algebra. So first we use algebra. Then we can use a u substitution to change this x plus 1 into, say, a t. And then we can use an inverse trig function to solve it. So now we're going to move on to an example video, which is where the meat of this is going to be. And what we're going to do is show how the triage process works when we're faced with integrals that we don't recognize as being associated with a particular section. After all, it's easy to know that you're using inverse trig substitution when you're in the chapter that says inverse trig substitution on the top of it. It's much more difficult to identify what to do if you're in a chapter that just says, here's 86 integrals, solve them as you will. All right, so I'll see you for the next video.